can all agree that the fire detection and alarm system, or an FDAS, is a must in any establishment. Numerous types of FDAS exist, like the conventional and addressable fire detection systems, but what if there was a less expensive and less complicated method of installing fire detection and alarm systems in homes and in buildings?
Our undergraduate thesis aims to create a web-based fire detection and alarm system, or FDAS, to decrease the number of wired connections, to increase the flexibility of fire detection systems, and enable it to be controlled with just a tip of a finger.
I'm Nicole Hayag,
I'm Laura Giselle Onato,
and we are from De La Salle University, Dasmali.
College of Engineering, Architecture, and Technology.
In this video,
we will talk about the components of the
web-based
fire detection and alarm system,
the software behind it,
and basically how the whole system works.
So, let's get right on to it. Good day to our thesis panel, thesis advisor, and to everyone watching this video. Welcome! To give a solid foundation to the discussion of our undergraduate thesis, we would like to start off this presentation with our objectives. Our general objective is to create a web-based fire detection and alarm system.
The specific objectives are 1. To create a 3-level alarm and a web-based application which will serve as the control panel. 2. To interface the connections, such as IoT servers and gateways, of IoT devices to be used in the system. 3. To design an electronics plan for the system with proper IP addressing schemes and device locations, including the location of access points.
Number 4. To build a mock-up of a 3-story building with 2 rooms per floor and 6 smoke sensors located in 6 rooms, and to test the functionality and accuracy of the system using a smoke detector tester. Number 5. To evaluate the system by providing questionnaire to at least 3 professionals such as professional electronics engineers. The web-based FDAS adopts the use of wireless RF433 smoke detectors, which sends RF signals once they detect the presence of smoke. These RF signals are converted by the son of bridge to Wi-Fi signals, which are then recognized by the router where the bridge is connected. Like the standard and existing FDAS, this system is also incorporated with a manual pull station, strobe lights, and a fire alarm bell, which are also connected to the Raspberry Pi through a relay module.
Our web-based control panel is powered by Home Assistant installed on a Raspberry Pi. The user interface or UI of Home Assistant is called Longares, and it serves as the web application for the system. The UI for the web-based FDAS consists of 4 pages: Home, Fire Alert, Control Panel, and Recent Alarms page. The home page displays a digital strobe light and an image which indicates smoke detection. The home page only displays minimal features but huge images so that the alarm can be seen even if the user is somehow far from the screen. The default theme of the UI is set to cool blue. Whenever smoke is detected, the color of the theme changes to fire red, and for the home page, the strobe light will turn on and the image will change from no smoke detected to smoke detected.
Alarm 2 detected smoke.
The strobe light is also clickable and will navigate you to the fire alert page. The fire alert page consists of 3 features: fire level, fire location, and the building. The fire level indicates the level of fire that is happening within the building. The fire location gives the floor numbers and room numbers where smoke or fire is detected.
Alarm 3 detected smoke.
The building displays a two-dimensional model of the building and shows a fire icon on a certain room where smoke or fire is detected. All fire icons are clickable. When clicked, a confirmation text will show up to verify if fire is out on a certain room. At fire level 3, the Home Assistant will send data to our Node-RED flow to trigger the fire alarm bell and strobe light connected to the Raspberry Pi's GPIO pin. The number 3 during fire level 3 is also clickable and will navigate you to the control panel page. The control panel page has a digital pull station that acts as a button to deactivate fire level 3 alarms. Once clicked, a cancelable confirmation text will show to verify the deactivation of alarms. The button will send data from Home Assistant to Node-RED to turn off the fire alarms.
Alarm 6 detected smoke. Fire level 3.
The page also consists of toggle buttons to activate or deactivate smoke detectors. If a certain toggle button were toggled, the smoke detector corresponding to the toggle button will be deactivated, and Home Assistant will not receive alarm notifications from that specific sensor.
Alarm 5 detected smoke.
The page also displays a 2D model of the building, which shows the deactivated and activated smoke detectors. The status of the SON-OFF RF bridge is also included in the page for monitoring. It updates if the page is refreshed. The last page is the Recent Alarms page. It just shows the recently triggered smoke detectors. Remember to verify if all fire or smoke are out on the fire alert page. Once done, the theme will change back to its default cool blue color.
The web application is programmed in Home Assistant's Lovelace UI using YAML programming language. The YAML programming language is commonly used for configuration files and in applications where data is being stored or transmitted. The Lovelace UI raw configuration editor is edited using YAML to create the 4 pages of the web application with their own features. The configuration.yaml file is the main YAML file used to gather all of the information for the web application's configuration. The SON-OFF or eVoLink credentials and themes are included in this syntax. Node-RED is also enabled here. The automations.yaml file includes all the codes to automate a certain service once triggered. This contains the automations of creating alarm notifications that communicate with Node-RED. The Node-RED flow for fire level 3 is programmed using JavaScript by translating our 81 calculated combinations of alarms for fire levels. Node-RED receives data from Home Assistant and translates it to 1 or 0 depending on the presence of smoke. An AND-gate node is used on combinations of 3 different alarms to know if fire level 3 is up or not. This gate node is essential to trigger the Raspberry Pi's GPIO pin where the fire alarm bell and strobe light are connected. A momentary switch node also communicates with Home Assistant to deactivate fire level 3 if fire is already out.
To test the functionality of the system, the web-based FTEST was simulated through a mock-up of a 3-story building with 2 rooms per floor and a smoke detector placed in every room. In all tests, the smoke detector was triggered with a smoke detector tester. The web-based F-test responds to 3 alarm levels, the first level being raised at the trigger of 1 smoke detector, the second level being raised at the trigger of 2 smoke detectors, and the third level being raised at the trigger of 3 smoke detectors. The fire alarm bell and strobe lights are specifically triggered at the third level alarm only. In the next few video clips, we will show you how we simulated our tests and gathered our data. Simulations of all 3 levels were done in 10 trials for each smoke detector, which resulted to a total of 180 trials.
To simulate the first fire alarm level, we must trigger 1 smoke detector. In this case, we chose smoke detector number 3. So when the smoke detector senses smoke from our tester, the home page of the web application turns into red, indicating that smoke is detected. The fire alert page shows the fire level, which is 1, and the fire location, which is the second floor, third room. This is also seen in the notification panel at the sides of the mockup. To simulate the second fire alarm level, we must trigger 2 smoke detectors. In this case, we chose smoke detector number 2, which is found on the first floor, and smoke detector number 3, which is found on the second floor. Once the second smoke detector is triggered, the fire alert page updates the fire level to the second alarm, and it also updates the fire location, thereby showing 2 locations of the fire. Both of these are seen at the web application and the notifications panel. To simulate the third fire alarm level, we must trigger 3 smoke detectors. In this case, we chose smoke detector number 1, smoke detector number 6, and smoke detector number 4. Once the third smoke detector is triggered, the fire alarm bell and the strobe lights will turn on. The fire alert page will update the fire level to the third alarm and update the fire locations as well. On the control panel of the web application, we can deactivate the fire level 3 alarms to turn off the fire bell and the strobe lights. In addition to these simulations, we also have the manual activation of the system, where we have a manual pull station which can trigger the fire alarm bell and our strobe lights when needed.
Results from our trials show that the response time of the RF433 smoke detectors has a range of 0.54 to 4.52 seconds and an average response time of 1.52 seconds.
On the other hand, the response time of the system notifications from the time the smoke is detected by the sensors has a range of 0.07 to 3.83 seconds and an average of 1.45 seconds.
The factors that affect these delays are the following: the distance of the smoke to the smoke detector, the amount of smoke released, and the internet connection speed.
To conclude, the total response time of the system from the release of the smoke to its corresponding alarm has a range of 1.53 to 6.08 seconds and an average of 2.96 seconds. Aside from testing the system through a mock-up simulation, an evaluation from a professional electronics engineer was also accomplished. This was done by sending a video presentation and online questionnaire to the respondent. Responses taken showed positive feedback and a strong agreement that the system is indeed accurate, functional, significant, and has satisfactory performance.
To conclude the first objective, the web-based application was designed and programmed in such a way that it will notify users of smoke detection if they have Wi-Fi connection. For the second objective, Node-RED was the answer to interface fire alarms and the Raspberry Pi to the web application. There were 81 calculated combinations for the fire levels, which were used in the web-based application in the Objective 1 and also in the Node-RED flow in Objective 2. For the third objective, the physical topology of electronics plan was designed using AutoCAD, One access point is placed on each floor, and the wireless smoke detectors are placed on 2 rooms per floor. The symbols used were based on PECE's ICT Terminology Handbook version 2, and the specifications used were based on the Philippine Electronics Code Book 2 for FTES.
The logical topology, designed using the Cisco Packet Tracer software, shows all the wired and wireless connections, as well as the IP addressing scheme used, which is IPv4. For the fourth objective, the study concludes that the system functions properly and that the system is accurate following the NFPA fire code of having a 10-second allowable response time. Finally, the results under the fifth objective further conclude the system's functionality and accuracy, as well as its significant contribution and satisfactory performance. In addition, our recommendations include adding a battery status, floor plan, and manual pull notification in the web application, enable the system to function without internet connection, completely eliminate all wired connections, have the electronics plan be checked by a registered electronics engineer, test the system at an actual building or establishment, and lastly, gather additional feedback and evaluation. Thank you for sharing your time with us. We would appreciate any comments and suggestions. Just let us know. Again, I'm Nicole Hayag.
And I'm Lara Dizil Onato.
And this was the web-based fire detection and alarm system.